morning, everyone, and thank you for attending my presentation, which is about silicon carbide micro-hot wires for flow measurement in harsh environments. Before starting my presentation, I want to introduce it by talking about turbulence. I think you are all familiar with turbulence in the planes. But to explain it a little bit more, I borrowed this explanation from Richardson, who is the guy who invented modern weather forecasting. So he wrote this little poem: big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So what does this mean? Say you have a structure which is plunged into a fluid, say a car, plane, train, and it will inject mechanical energy at its specific scales, like 10 meters for the plane, and then there will be an eddy energy dissipation cascade, which means that the bigger eddies will break down into smaller and smaller eddies up until this point of viscous dissipation, and then the mechanical energy of the fluid is transferred to thermal energy. And this happens at this eta, which is big L divided by Reynolds to the 3/4, which is called the Kolmogorov space scale. There is also a Kolmogorov time scale, which means that the smaller an eddy is, the faster it will oscillate. So down here is an overview of the Kolmogorov time and space scales for different applications. So the faster the fluid will be, and the smallest the turbulence will be, and the faster it will oscillate. So say for the aircraft, it's kind of the worst case. You can have eddies which are 10 microns across and which oscillate to 100 kilohertz. So small phenomenon, fast phenomenon, it's not the easiest thing to measure. So how can we do it? Upon all the flow measurement techniques, thermal anemometry, seems to be a good one. So the principle is the following: say you wet your finger. If you feel it cool down, it means the wind is blowing. So this is the exact same principle. So we have this little element which is heated by Joule current. It generates a small pocket of air, which is called a thermal boundary layer. And when the wind is blowing, it will displace this boundary layer, thus cooling the wire by forced convection. So by knowing the temperature of the wire, we can have an image of the flow, and we can have an image of the temperature by measuring its electrical resistance, given we know the TCR of the material. TCR is temperature coefficient of resistance. So the higher it is, the more sensitive our system will be. And we can plug this into a CTA loop, a control loop, to have better performances. And what's good about this technique is it's easily miniaturizable. Like you have no moving parts, and it is like the easiest to reach these small and fast Kolmogorov microscales using this technique. So before jumping back in, I just will summarize my presentation. I'll talk about my context, which is harsh environments. Then I'll present our realization, silicon carbide hot wires. Then I go on to explain some characterization and some first wind tunnel experiments that we made before concluding. So why we need to measure in the first place? So I think you all know that Navier-Stokes is a millennium problem. So $1 million, for who can prove the existence and uniqueness of the Navier-Stokes equations. So people, in order to optimize geometries for planes, car, trains, they need to do real-life measurements. Like they do small-scale models. They put them into wind tunnels. They generate data with sensors, and then the data is fed back into into simulation models in order to better understand turbulence and implement flow control strategies. But then what happens inside a turbojet engine? Like, you cannot put a sensor into these 1000 degrees hot reactive gases. It will instantly burn, it will instantly melt, and so the traditional metal probes are not suitable because the environment is too harsh. So this is my problem. We need to measure in order to understand turbulence, but we cannot do it for environments like these. So my approach to tackle this problem is by studying a new material, which is silicon carbide. It is a really tough ceramic. So people do silicon carbide MEMS like for the past 25 years. NASA has a whole research topic for instrumenting space missions on Venus and Mars, which are pretty harsh environments. And so they make cantilever anemometers out of silicon carbide, and they also make full IC electronic chips on silicon carbide. So what's great about SiC, it's wide band gap, which means then when you heat it up, it won't conduct current as easily as silicon. It won't short. Really, really high sublimation points and near inert surface chemistry. So perfect for my turbojet engine. So this is what we've done. So we did this little wire, silicon carbide wire, which is 100 microns across, 6 microns wide, and 0.8 microns thick. So you may ask why this complicated structure, like why this silicon carbide, silicon glass sandwich. There are two stakes here. In order to work properly, our wire needs to be suspended. It cannot lie on a substrate because we want all the thermal dissipation to happen in the fluid and not to be soaked into the substrate. And the second problem is that silicon carbide is grown with epitaxy, and it cannot be grown on anything other than silicon. Like, we have to match the crystal structure. It cannot be grown on silicon oxide. It cannot be grown on glass. So we have this silicon carbide on silicon thing. And when we do our system, like we tried it, we have these huge current leaks through the substrate. This is a problem, like people who want to do silicon carbide hot wires, they know this problem, and it's really hard to overcome. And our solution here is to make a sandwich, like to make a sandwich of silicon, and the real substrate is Borofloat 33 glass. That means that when we probe our wire, the current is only in the SiC, so in our sensing material. So does this work? Sorry, I will explain a little bit more the flow chart for this structure. So we start with bulk silicon substrates. We grow silicon carbide on it, and then for the sandwich part, we grind the backside of the silicon to 50 microns thick, and then we anodically bond it to a glass wafer, and then we do our device contacts, silicon carbide patterning, and then underetching to achieve wire liberation. So does this work? Well, these are some characterizations that we made. So remember, we want to measure the TCR. That's the like sensitivity of our sensor. So we did put it on a temperature hot plate, and we measured it for temperatures ranging to like ambient to 500 degrees. And we observed this really specific resistance behavior with an extrinsic domain and metal-like domain, which is typical of semiconductors. And so this is like a validation of what we did works, because we can fit this law like this in the extrinsic regime. When you heat the material up, the dopant will generate carriers to following this regime, and in the extrinsic domain region, we can find like really good, we have a really good fit of this law, and we have like correct order of magnitude of dopant energy and alpha coefficient. So this is great. What about the TCR? So at ambient we have minus 700, and at 500 we have like plus 700. So not great, not terrible. Platinum for comparison is 2,800. So it is not as great as platinum, but it works. And to show further, to show that it can in fact measure airspeed, we took our little device and we wire bonded it onto a PCB that we flush mounted on a small scale wing. And so there is a current source which hits up the wire, and we measure the voltage with an acquisition card. And so this is we placed it into a small wind tunnel, which can blow up to 15 meters per second. And so what we observe is that we have a voltage drop of the silicon wire from 0 to 15 meters per second. So remember, the wire is cooling because of the flow, so the resistance, the electrical resistance decreases because we are in negative TCR. So this is just to compare it to a traditional hot wire probe. And so this is a demonstration that silicon carbide can work as a sensing material to measure flow. And it can indeed detect flow speed variation. So what is there to conclude about this? Silicon carbide can work for ambient temperatures and for hot flows, maybe further than 500 meters, 500 degrees. And what we need to do next is to optimize the sensitivity to achieve better TCRs than 700. We can do this by changing dopant concentration, by trying different things on the material itself. And then we have to calibrate the sensor in proper wind tunnels in order to determine the real wall shear stress response of the sensor. And of course, then we have to beat it up a little bit more on real hot and corrosive gases to see if it is really suitable for harsh environments. That's all for my presentation. Thank you for your attention.